Okay, so continuing with our heat or our enthalpy reactions, we're going to look at how to manage a reaction when there's stoichiometry involved. Now, these are called thermochemical equations. Okay, they're kind of specialized because they also include the delta H value in the reaction. So for these, I mostly will expect you to be able to just read the reaction and know how to manage them from here. But let's talk about what thermochemical equations are first. Okay, this is a balanced equation. Okay, and the big difference here is that it also involves or tells you the delta H of reaction. Okay, and that delta H of reaction has a sign. The sign tells you whether the reaction is exothermic or endothermic. If you have a negative delta H, then the reaction is exothermic. So you don't have to try and figure out what your surroundings or your system are in these cases. You just need to find the sign. If you have a positive delta H of reaction, then that's going to be endothermic. Okay, so no trying to figure the system and the surroundings, thankfully, here. And so this delta H, this value that you're given, is proportional to the amount of the substance. So most of these delta H's that you're going to be given are going to be related to the balanced equation. We know from the balanced equation how much heat is released or absorbed. Okay? And that delta H is proportional to the amount of the substance. And we'll look at that again in a minute. And so we're going to also, for stoichiometry purposes, we're going to figure out a different ratio. And that ratio is going to be, instead of a mole to mole ratio, it's going to be a heat to mole ratio, or an enthalpy value, either way, heat to mole or mole to heat. I'm going to make this screen a little bit smaller so we can see all of the things that are on here. There we go. So I want to talk about exothermic and endothermic one more time. Okay. So let's think about exothermic reactions. Sometimes those are easier if you include them in part of the reaction. So we can write a reaction, reactant to products, just any old standard. Okay, and if we're told negative delta H value, whatever it is, we can look at this reaction and we can know that the heat is being released because it's exothermic. If you were to rewrite this, you can write reactants to products plus heat, or the delta H value can be here, or some people just use delta, or you could say enthalpy, or you could just say heat, whichever. Okay, any way that helps you remember that the heat is coming out of the reaction. What if we're given an R goes to P, but this time we're told we have a positive delta H? Okay, well, in that case, this is an endothermic reaction, and that means that in order for the reaction to go, it's got to absorb some heat. And so you can rewrite this as heat, using any one of these possibilities here, heat, plus reactant forms product. Okay, and that may help you see better about what's going to happen, what you expect to be happening in these cases. Okay, so let's see. Let's do a couple of examples. Oh no, I guess not quite yet. Let's think about what enthalpy is affected by. Okay, because these values change depending on what you do to your balanced chemical reaction. So first of all, the amount of the material counts. Okay, if you have 100 grams of something and it releases 1,000 kilojoules of heat, Well, then having 200 grams, you'd expect to get 2,000 kilojoules of heat. Okay, so it's proportional. Okay, the heat's proportional to however much you use. Also, if you go in one direction, for example, you go from A to B, and you measure that you released 100 kilojoules of heat, then you could hypothesize or predict that instead of going from A to B, if you turn that reaction around and go from B to A, that the value of the delta H will be the same because nothing's changed about the amount, but the sign will be different. Now it's going to be a positive sign. And reactions are additive. Okay, this is part of Hess's law. Okay, and in Hess's law is used when it's really hard to figure out or get an answer directly. For example, we might want to know what happens from A to C and how much energy there is, but we don't have a direct way to figure that out. It's some kind of complicated reaction that we can't really measure very well. But for example, if we can measure A to B, okay, and then we know that B to C is some value, then we can also figure out that A to C, because B is going to drop out here, will give us this total value. Okay. Now, why can we do that? Under what principle do we get to do that? Just a brief talk here. Actually, let's skip that. I'll extend this page for a minute. Okay, so remember that enthalpy, or change in enthalpy, is oh, finally, I'm sorry, it came to my head. A state function. Okay, it's a state function, which means that it doesn't matter how enthalpy got to where it was. Remember when we're raising our hands and lowering our hands and being still and so forth. It doesn't matter how we got to that position. That's just where we are. And it makes no difference how it happened. So in that case, it's okay to just add up things and things that you know, because the delta H, the enthalpy for your total value, will be equal to the delta H of reaction 1 and plus the delta H of reaction 2 plus however many you have. So you just add them up, and however much that energy was, you're going to get the total heat energy that is going on in the reaction of interest. All right, so some examples. We've got methanol forming carbon monoxide and hydrogen gas. Okay, 1 mole here and 1 mole here are both implied, and then we have 2 moles of this. And we're given the amount of heat. So you'll typically be given these in the thermochemical reaction. So the first question is, heat absorbed or released? Because you don't have to do anything but look at the sign. All we care about is the sign right now. That's positive. That indicates it's endothermic. And therefore, heat has to be absorbed. All right, if you needed to rewrite this, you might write heat, that's just my heat sign, plus the methanol forms carbon monoxide and some hydrogen gas. Okay, so that would indicate, the sign indicates what the reaction is. All right, so let's do a little stoichiometry now. I want to show you a strategy that you're going to use over and over and over for these, and it's similar to what you've done before. And I also don't want you to worry. If you didn't quite get this as well as you wanted to in Unit 2, you can still do this. This isn't very complicated. All right, so we're going to have a setup. The strategy looks something like this, where we'll go from grams of known to moles of known, because there's just no getting away from changing into moles. And then we're going to use a heat to mole ratio to get to the amount of heat, or delta H. Okay, so this will need a molar mass, and this one needs that heat to mole ratio. Okay, so let's look at an example of this. What can we figure out given the information we have? Well, let's make some equalities that might make life a little easier. One thing I know is that for every 1 mole of methanol, I'm going to need 90.7 kilojoules of heat. Okay, so that's an equality. We can set that up as a conversion factor with the moles on the top or the kilojoules on the top, depending on what we want to do. And also we need to have a molar mass. So 1 mole of methanol is also equal to 32.04 grams. Okay, so if you add up an oxygen, a carbon, and 4 hydrogens, this should be the mass you get for this. All right, so let's do one little bit at a time here. So, for example, we'll start with 45.0 grams of methanol. All right, and then we're going to convert using our molar mass to the moles of our known. So in this case, this will be times 1 mole of methanol for every 32.04 grams. Notice that we don't have grams anymore. Where are we trying to get? We're trying to get to an enthalpy value here. Enthalpy would have been better than heat as a word, but anyway. 45 grams times, so here we are to 1 mole after we divide by 32.04. Now, we can take this lovely heat to mole ratio that we set up right here. What we want to know about is heat, and what we want to get rid of is the mole. So I'm going to put 1 mole of methanol down here. And I know that there's 90.7 kilojoules from the thermochemical reaction. So now I've gotten rid of the mole, and I'm only to a value of heat, which is what I was looking for. And so if I don't use 1 mole of methanol, but instead some other amount of methanol, which actually turns out to be 1.4 moles, I get plus 127 kilojoules of heat that I need for this reaction. Now, I want to note for you, okay, that we've got to think about when there's not a 1-to-1 ratio, okay, 1 mole to some amount of heat ratio. So let's look at a little bit different problem. In this case, we'll do what amount of enthalpy when 240 grams of H2 are produced. Okay, so this is one of the products, all right, but the difference is now we have a different mole ratio. Unfortunately, I can't pull that screen back down, I don't think. Nope. But you can see it. So notice that we have plus 90.7 kilojoules for every 2 moles of H2. Okay, so because there's a 2 as a coefficient in the balanced equation there, we've got to take this into account. Now, there's no place that shows you this. You have to be able to do this on your own. Okay, and we also know that 1 mole of hydrogen is 2.018 grams. So now we're ready to answer this question. Okay, but it's important on this mole to heat ratio that we're thinking about, because now we have the 2 moles to deal with. All right, so we are starting with 240 grams of hydrogen. Like always, you can't do anything in grams, so we're going to transfer that to a mole, and that's divided by 2.018 grams. And now we want to use this heat to mole ratio, and I need to get rid of moles of H2. Okay, so I've gotten rid of the grams, and now I need to get rid of moles of H2, but I can't just write 1 mole of H2 because there's 2 moles of H2 produced in this reaction and 90.7 kilojoules of heat. And so when you finish this, I got 10,786 kilojoules of heat that is absorbed when this reaction happens. This should be a positive. And I know that's not sig figs, but for now, I don't care. All right, so let's now look at a little bit different setup. Okay, now we still are back to the same reaction that we were given just a minute ago. But you need to read reactions, okay? The question says, how much heat is transferred if 45 grams of H2 is used, okay, to form methanol? So actually what we've done here is turn this reaction completely around, and instead we'll have CO plus 2H2 forms methanol. What do we need to do with the delta H value for this reaction? Well, we reverse the reaction, so now our delta H is a negative 90.7 kilojoules. Notice it's the same value, but because we reverse the reaction, it's going to be a negative number. So you've got to be watching out for reading the question, because the question asks you about the opposite reaction. All right, so again, we've got hydrogen, and so our mole to heat ratio here is minus 90.7 kilojoules for every 2 moles of H2. All right, and so if I want to get from 45 grams to the amount of heat that it takes, I'll start with 45 grams of H2 times 1 mole of H2 over its molar mass, 2.018 grams. Okay, and now I'm going to take this lovely equality I just wrote up here times minus 90.7 kilojoules for every 2, don't forget the 2 moles of H2. All right, so I'm going to get rid of grams, I'm going to get rid of moles, and I'm going to end up with units of kilojoules. And so I get minus 2.0 times 10 to the 3 kilojoules there. All right, another example, only this time we're starting by being told for this reaction that we get 400 kilojoules of heat released. Okay, I don't know where that came from. Oh no, that's right, minus 91.8. I'm sorry, that's right. That's this value for ammonia forming nitrogen gas and hydrogen gas. All right, so in this case, we want to know how much ammonia was used if we get 400 kilojoules. So in this case, we're going to go from, and this tells you grams right here. Be careful, that's gas and that's grams. We're going to go from kilojoules, in this case, to moles to grams. Okay, so basically we're working backwards from where we were once before. So let me see. We've got an equality that says negative 91.8 kilojoules is equal to 2 moles of ammonia. Okay, that's from our balanced equation. I know the enthalpy, and I know there's 2 moles because the coefficient is 2 here. So in this case, and I also have a molar mass of 17, NH3 is 17.04 grams per mole. Okay, so I'm going to use that too. So in this case, 400 kilojoules is released. Okay, so that means minus 400 kilojoules. That's what I know, and that's where I'm going to start. Minus 400 kilojoules of heat is released during this reaction, and then I need to get to grams. So I need to get rid of kilojoules down here using my lovely heat to mole ratio. Okay, so that's going to be 2 moles of ammonia for every negative 91.8 kilojoules of enthalpy. And then it asked me for grams, so I'm also going to convert to grams. So that'll be 17.04 grams for every mole of ammonia. And that works out to be equal to 74.2 grams of NH3 used. Oops, NH, whatever that is, I mean NH3. All right, so let's look at these 2 kind of strategies you worked with for a minute. The first strategy we looked at, the one we spent the most time on here, is we began with grams, okay, and we're going to convert to moles using the molar mass. And then we're going to convert to enthalpy, okay, some value by using the heat to mole ratio. That's the first thing we did several times. Now I want you to look at what we just did. In this case, all we did was work backwards in this particular problem. Okay, we had to switch our conversion factors. So that means you got to think, I have kilojoules on the top. I want to get rid of kilojoules, so let me put those on the bottom. And then that gives you a mole ratio to help you get rid of that, and then you can end up with grams. So all we did is basically a 2-step process here. Figure out what you know, and then convert to a mole, or if you start with a mole, then I guess you don't have to, and then convert to the delta H. If you start with heat, work backwards towards the grams.